Hi, my name is Gupta Khan, and in this video, we're going to look at the phase relationship between voltages and currents in an inductor resistor circuit. We're using the Phet AC kit, so that's an AC battery or AC supply, that's a switch, that's a resistor, and that's an inductor. And I've got three traces here. So this one is looking at the current, we'll be looking at the current in the circuit. This one is the voltage and time graph for the resistor. And this one over here will be the voltage time graph across the inductor. So let's see. Now, let's compare the current and the voltage across the resistor. If you look at the trace over here, these two traces are becoming maximum at the same time, and they become minimum at the same time. Let's just stop it for a second. So current is maximum in the circuit and voltage across the resistor is maximum in the circuit, or we say that current and the voltage across the resistor, they are in phase. Whereas if you look over here, if we compare the voltage across the resistor and the voltage across the inductor, they're not in phase. So this one is at its maximum value, whereas the voltage across the inductor had reached the maximum value a little bit earlier, and it is reaching almost zero, or we say that this one, voltage across the inductor, is 90 degrees ahead of the voltage across the resistor. Let's run it again and stop it. Okay, now here, okay, so current is zero at this particular instant. Voltage across the resistor is zero, or they are in phase, and we can see from the shape of the previous values. And if we now compare the voltage across the resistor and voltage across the inductor, this one is zero, but this one had passed a zero value a little bit earlier. And if we look at this time from here to there, that is quarter of a cycle or 90 degrees, or in other words, we say that voltage across the inductor is 90 degrees ahead of the voltage across the resistor or the current. Let's look at some notes now. So here, all three graphs are done on the same axis. So that's the current time graph. The blue one is the voltage across the resistor, and we can see that current and voltage across the resistor, they are in phase. They become maximum and they become negative maximum at the same time. But if we compare the voltage across the inductor and the current, so voltage across the inductor is 90 degrees ahead of the current or the voltage across the resistor. What's the reason for that? So if we look at the current time graph, voltage is induced across the inductor only when the current is changing, or VL is proportional to the rate of change of current, or the gradient of this current time graph. So here at this particular instant, the gradient of the graph is almost flat. So therefore, voltage across the inductor is zero. Whereas somewhere over here, the gradient of the current time graph is maximum. So at this position, voltage across the inductor is maximum because the rate of change of current is maximum. Now, if we want to relate these two voltages, voltage across the inductor and the voltage across the resistor, to the supply voltage, or for the AC battery or the AC generator. So we draw what we call as phasors or vectors. Conventionally, voltage across the resistor is always drawn here. If we have to draw the current phasor, that will be also along here. Voltage across the inductor is across here, and these phasors always go or move in an anti-clockwise direction, or their angular velocity is anti-clockwise. So we can see from here also that voltage across the inductor is 90 degrees ahead of the voltage across the resistor. So if we want to add them together, we have to add them in a vector manner. So the voltage supplied by this one is shared by these two, but because they are not VL and VR, they don't become maximum at the same time or minimum at the same time, so they are added in a vector way. And how do we add these in a vector manner? So VL square plus VR square will give us the V supply or V generator. So that's the supply voltage. Now, current will always be here. So because these phasors go in an anti-clockwise direction, so we can see that supply voltage is ahead of the current by these many degrees. And how do we find this angle? By using tan theta, which is VL over VR. Now, what do we mean by the impedance of an inductor resistor circuit? Is the total reactance of the inductor. And remember that impedance changes with the frequency, because the reactance of the inductor will change with the frequency. And because voltages are not in phase, therefore their reactance of the inductor and the resistance of the resistor, they are not in phase either. So we'll add them in a vector manner. Just we added voltages, and Z square, which is the total impedance of the inductor resistor circuit, is XL square plus R square. So we can use this formula to calculate Z. And again, to find the angle between the current is drawn here, Z is over here, we will find tan theta, which is XL over R. Now, to solve the problems, inductor resistor circuit problems, so first thing we need to do is, if we have to find the current in the circuit and the voltage across the inductor and the voltage across the resistor, and now we are talking about the RMS values, what will be the RMS values? So first of all, we will calculate the reactance of this inductor by using the formula XL equals 2 pi FL. Then we will add these two resistance and reactance of this one and the resistance value in a vector manner using Z square equals R square plus XL square. And to find the current is generator voltage or supply voltage divided by the total impedance. So once we've got the current, then we can find out VL. Sorry, this one should be VL. VL should be equal to current times XL, and VR should be I current times R. So that's how we can solve this problem. So thank you. That's all for today's video.